All right, so we're going to work a surface tension problem. This is problem 167 from your textbook, and I'll read it. It says the triangular glass rod has a weight of 0.3 newtons and is suspended on the surface of the water, for which the surface tension sigma is 0.0728 newtons per meter. Determine the vertical force P needed to pull the rod from the surface. Okay, so we're trying to get this vertical force P that's required to pull this system out of the liquid. And the glass rod that's mentioned here is these three triangles, and those three triangles are literally sitting right on the surface of the liquid. In this case, the liquid is water. Okay, so in order to pull these rods out of the liquid, what we need to do is we need to overcome both the weight of the rods and also the force due to surface tension. So step number one of problems is always draw a diagram, visualize what's being asked. So we have a diagram here, it's drawn, but it doesn't tell us everything we really need to understand to solve this problem. And to sort of address this problem, you really need to have a sense for how surface tension is acting to pull down on this rod as it's being pulled out of the water. So what we're going to do is we're going to draw each of these rods. An example of one of the rods. This could be one side here. Okay, so that's a rod. I've given it a length L. It might have some diameter D. Okay, so that's an example of the rod that makes up each of the three sides. And so when that sits in the liquid, and is pulled up, we're going to have an interface like this one between the liquid, which is down here, and the air, which is above it. And so if we draw one more sketch, you can see this even better. Here's the cross section of the rod, which has some diameter D. And as we pull up, as the rod goes upwards, the surface tension is going to be attached here, and it's going to pull straight downwards. And it's going to look something like this. Okay? So here's our liquid below. Here we have surface tension acting up, pulling. The force on the rod is down, so we'll write surface tension pulling down in that direction as we're pulling up on the rod. Okay. So now I have a good sketch. I've got the rod being pulled up. I've got surface tension coming down. And so now I'm ready to write down some of the key concepts that I need to solve this problem. Okay, the first concept is just a force balance in the vertical direction. So that means that the force P acting upwards must be equal to the weight of the rod pulling downwards and also the force due to surface tension, and I'll write that as an F with a subscript sigma. Okay, so in this problem the weight is given, so I don't need to refine that any further, but I do need to express this force due to surface tension. Well, force due to surface tension is going to be equal to the magnitude of the surface direction times cosine of theta, where theta is the angle that the interface makes with the vertical. In this case, that angle is 0, so this is just going to be 1. Okay? And then, if we remember that sigma has units of force per length, then in order to get a force, we're going to have to multiply this expression by a length. So it's going to be the total length. We'll call that L total. Okay, so now I've got an expression for sigma in terms of some total length, and now we need to think carefully about what that length is. So we're going back to this diagram. I've got a length here, I've got a length here, and I've got a length here. So your first inclination might be that, okay, it's 3 times L would give me the length. But keep in mind that the rod has the liquid contacting it on both sides. So that means we have 3 rods, 2 sides per rod, and so this means that this expression can simply be written as 6 sigma times L. So now we put this back into our expression over here. P equals the weight plus 6 times sigma times L. And if you were to take this number and this number and this number, substitute in, you would be able to get your answer. Once again, going through our problem-solving approach, we have a diagram. It's really key to visualize what's going on. If you didn't visualize both sides of the cylinder being contacted by the liquid, you would get the problem set up improperly. Okay, so visualizing it, making sure you have a handle on the problem is really important. Identifying relevant principles and laws. In this case, we needed a vertical force balance, and we needed to recognize that the force due to surface tension was equal to the surface tension multiplied by a length. So that was our second key principle. So we rearranged those into an expression. Does it make sense? Well, if the surface tension gets higher, the force gets bigger. That makes sense. If the length of all the rods gets longer, the force gets bigger. So yeah, that is a model that makes sense. So then finally, you can substitute in numbers and get the answer.